Okay, imagine this. A computer instantly telling the difference between a scrawled 7 and maybe a hurried 1 on a bank check.
Right.
Or, sorting out a 9 from a 4 in a huge pile of postal codes. It seems almost magical, doesn't it?
It really does.
But today, we're not just looking at the magic. We're actually stepping behind the curtain. We're going into the fascinating world of support vector machines, or SVMs,
hmm
to see exactly how they tackle this kind of challenge.
And what's really fascinating here, I think, is that we're looking at one of the most powerful and, frankly, versatile supervised learning methods out there in machine learning.
Right.
So our mission today is to really embark on a deep dive into these SVMs, specifically how they're implemented in Python's scikit-learn library, which is, incredibly
Where
popular,
everyone uses it.
pretty much.
Yeah.
And we'll see them in action on the famous MNES dataset, that big collection of handwritten digits, sort of the benchmark for classification.
You've shared some incredible source material with us for this. We've got detailed conceptual slides laying out the theory,
Yep, the foundations.
and also a hands-on coding demo that really brings these algorithms to life.
Exactly, theory and practice.
So we're going to distill the most important nuggets, connect the dots between theory and practice, and hopefully give you a shortcut to truly understanding how these powerful algorithms work, why they can be so effective, and also, where they might fall short. There are limitations.
Crucial to know both sides.
Think of it as adding a really vital new tool to your machine learning toolkit, one you deeply understand. So, let's get started on this journey.
Let's do it.
So let's start right at the beginning. When we hear support vector machine, it sounds complex, right? Conjures up images of tricky math.
Yeah, it sounds intimidating.
But at its heart, the core idea is actually quite elegant, quite intuitive, isn't it? What is an SVM really at its essence?
Absolutely. At its core, an SVM is a supervised learning method.
Yeah.
It's known mostly for classification. That's its main thing. But it's also incredibly versatile. It can handle regression problems, finding trends in data, and even detecting anomalies or outliers, things that just don't fit.
Outliers, right?
The core idea, though, is beautifully simple conceptually. SVMs work by constructing a hyperplane.
Hyperplane. Okay, like a line or a surface.
Exactly. A line in 2D, a flat plane in 3D, or, well, a hyperplane in higher dimensions, or sometimes a set of them.
Uh-huh.
And the goal of these hyperplanes is to act as optimal decision boundaries. They effectively separate data points that belong to different classes.
Separate the data.
Yeah, imagine you have, say, apples and oranges scattered on a table. Red apples, green oranges.
Okay, visual.
A simple SVM in this 2D world would try to draw a straight line, that's our hyperplane here, that best separates the apples from the oranges.
The best line. Not just any line.
Not just any line. The best line is the one that maximizes the margin.
Margin.
Yeah, think of it as the largest possible distance, like a buffer zone, between the closest data points of each class.
Ah, a buffer zone.
And these closest data points, the ones literally right on the edge of this buffer zone, they're critical.
Okay.
We call them the support vectors. They're the VIPs of your data for the SVM. They literally support or define that decision boundary.
That makes so much sense. The buffer zone idea gives it robustness, right? Like a safety net.
Exactly.
So it's not just drawing any line, but the one with the biggest cushion. That makes the classification stronger for new data that might be close to the edge.
Precisely. That wider margin helps generalization.
But you mentioned high or infinite dimensional space. My brain kind of stops at 3D. How do apples and oranges suddenly live in infinite dimensions, and why?
Right. That's where the real cleverness, the trick comes in. You're right. Sometimes data just isn't separable with a straight line or a flat plane in its original space.
Like our apples and oranges all mixed up.
Exactly. What if they're totally intermingled on the table? Impossible to draw one straight line to perfectly divide them. This is where SVMs use what's famously called the kernel trick. It's not magic. It's a very clever mathematical shortcut.
A shortcut.
Yeah. The kernel trick implicitly maps the data into a much higher, often infinite dimensional space where it can be linearly separated.
Implicitly. So it doesn't actually calculate coordinates way up there.
Exactly. That's the beauty of it. It's like taking our tangled apples and oranges and maybe adding a new dimension like, I don't know, sweetness.
Okay.
You lift them into this new dimension, and suddenly what was a mess in 2D becomes cleanly separable by a flat plane in this higher space.
Wow.
And the kernel function lets the SVM find this plane without ever explicitly figuring out the coordinates in that super high dimensional space. Saves a ton of computation.
That is clever. So in scikit-learn, how does this manifest? You mentioned different types.
Right, in scikit-learn, you primarily interact with SVMs through three main methods: SVC, USVC, and linear SVC. SVC stands for C Support Vector Classification. This is your general-purpose workhorse, the one you'll probably use most often. It's built on the libsvm library.
Libsvm.
Yeah, it's a foundational library. Highly optimized, developed over years by experts like Chicheng Chang and Chi-Jen Lin. It's really robust for nonlinear kernels.
Got it. So SVC is the standard.
Pretty much.
Sure.
Then there's USVC, our new support vector classification, very similar to SVC, also uses libsdm.
New.
Yeah, the difference is it uses a parameter called new instead of the C parameter to control complexity. We'll get into C and new later, but new gives you a different angle on controlling errors and support vectors.
Okay, a different control knob. And the third one?
Linear SVC, linear support vector classification. Name says it all right.
For linear problems only.
Exactly. It's specialized and often much faster for linear SVMs. It uses a different library called liblinear.
Liblinear.
Yep, another highly regarded library specialized for large-scale linear problems. Super fast solvers. So linear SVC is great for huge data sets where, a linear separation is what you need.
And it has more options for penalties and loss functions, you said.
Right, more flexibility there.
So for us learners, it means we've got options. A standard, robust one, SVC, one with a different complexity control, new SVC, and a fast one for big linear problems, linear SVC, like different tools for different jobs.
Precisely. A whole toolkit, all aimed at finding that best separating hyperplane.
Okay, now that we have a handle on SVMs and their flavors, let's talk about the dataset, MNIS-EST. It's practically famous in machine learning circles, right?
Oh, absolutely. MNIS is a cornerstone, a benchmark for image classification. It's this huge collection of handwritten digits 0 through 9.
Perfect for testing classification.
Exactly. It's a great way to see how models perform on real-world, albeit slightly simplified, image data. And it's what our source material uses for the demo.
So what are its stats? How big is it?
Well, the full data set is pretty substantial. It has 60,000 images set aside for training the model.
60,000.
And another 10,000 images in a separate test set. Crucial for checking how one of the model generalizes to unseen data.
Right, the test set is key. And the images themselves.
Each one is a small grayscale image, standardized to 28 by 28 pixels.
28 by 28.
Tiny, but consistent. And importantly, each image comes with a label.
The actual digit it represents.
Exactly. An image of a 5, so it has the label 5. That's the ground truth for supervised learning.
So if you picture that 28 by 28 grid, that's 784 individual squares, right?
Correct. 784 pixels.
And each pixel has a value, 0 to 255, showing how dark it is. All those numbers together make the digit. That's a lot of info per digit.
It is. And that leads us right to pre-processing. You can't just feed that 28 by 28 grid directly into most SVMs.
Why not?
Because they usually expect a flat, one-dimensional vector of features, not a 2D grid.
Ah, okay. So first step, flattening.
Exactly. Flattening or reshaping. Each 28 by 28 image gets converted into a single long vector.
How? Just line up all the pixel rows.
Pretty much. Concatenate the rows. So 2828 gives you 784 features per image.
So our 60,000 training images become a matrix of 60,000 rows by 784 columns.
Precisely. And the 10,000 test images become 10,000 by 784. It's a fundamental transformation.
So the machine sees a long list of 784 numbers, not really an image. Wow, 784 columns is a lot of features.
It is. And after flattening, the next crucial step is normalization.
Normalization. You mentioned the pixel values are 0 to 255.
Right. So we normalize them, usually by dividing each pixel value by 255.
Why divide by 255?
That scales everything neatly into a range between 0 and 1. A black pixel, 255, becomes 1. A white pixel, 0, stays 0, and grays fall in between.
Okay, but why do we need to do that? Why not just use the 0 to 255 values? Seems like extra work.
That's a really important question. It gets at how these algorithms actually learn. Normalization helps because algorithms like SVMs often perform much better when input features are on a similar scale.
Similar scale, so they don't get confused by big numbers.
Exactly. If some features had huge values and others small ones, the big ones could dominate the learning process, making the algorithm think they're more important just because they're bigger.
I see. It biases the learning.
Precisely. By scaling everything to 0, 1, we ensure the distance calculations inside the SVM, which are key for finding that hyperplanar fair across all 784 features. It levels the playing field.
Makes sense. Fair treatment for all pixels.
One last point on the data. Our source material, for demonstration purposes, uses a subset.
Smaller piece.
Yeah, just the first 10,000 training images and the first 2,000 test images, just to make the code run faster for the examples.
Ah, practical for demos and quick experiments. Saves time.
Totally. A common practice. But for a real robust evaluation, you definitely use the full data set.
Right. Good caveat. Okay. Data prepped, flattened, normalized. Ready for the main event. SVC. This is the workhorse, you said.
It is the general purpose powerhouse.
So how do we actually use it? And what are those knobs we can turn, the parameters?
Exactly. Using it in scikit-learn is super easy. You just create an SVC object, then call its fit method with your training data, xtrain, and labels. Yeah, train.
Simple enough.
But yeah, the real power, the difference between okay and great, comes from understanding and tuning its parameters.
Okay, let's dive into those. What's the first big one?
The C parameter, regularization parameter. This one's crucial. It's a float value. Default is usually 1.0.
C, regularization. And it controls margin hardness. What does that mean practically?
Think of it as a trade-off. It balances having a smooth, wide margin, that buffer zone, against correctly classifying every single training point.
So a trade-off between being robust and being perfect on the training data.
Exactly. A small C value encourages a wider margin, even if it means misclassifying a few training points. It prioritizes generalization. Stronger regularization.
Small c, wider margin, more robust, stronger regularization.
Downversely. Conversely, a large C value pushes the SVM to classify all training points correctly, even if it means a narrower margin and potentially a more complex wiggle boundary.
Large C, narrow margin, potentially overfitting. Weaker regularization.
You got it. Large C means weaker regularization, higher risk of overfitting by fitting the noise in the training data. It uses a squared L2 penalty, technically, to penalize complexity.
Okay, C controls that fundamental trade-off. What's next?
The kernel parameter. This is huge. It determines the type of hyperplane, how the data gets mapped using that kernel trick.
Ah, the kernel trick again. So this chooses how we map to that higher dimension.
Precisely. The default is RBF, radial basis function. Very powerful, common choice for nonlinear data.
RBF, what else?
You've got linear for straight lines, poly for polynomial curves.
Polynomial, like curves.
Yeah, and if you choose poly, you also set the parameter degree 2 for quadratic curves, degree 3 for cubic, and so on. Controls the complexity.
Or more knobs.
Right. There's also sigmoid, and even pre-computed if you want to supply your own custom kernel matrix based on your domain knowledge.
Wow, flexible. So kernel choice is key for handling nonlinearity.
Absolute paramount. It dictates the shape of your decision boundary.
Okay, C in kernel, what else?
Gamma, the kernel coefficient. This applies mainly to the nonlinear kernels like RBF, poly, and sigmoid.
Gamma, and it defines the influence of a single training example.
How so? Think of gamma as controlling the reach of each point's influence. A small gamma means a large influence radius points affect the boundary far away. Leads to smoother, simpler boundaries. Might underfit if data is complex.
Small gamma, wide influence, smooth boundary, like a wide-angle lens.
A good analogy. And a large gamma means a small, localized influence radius. Each point only affects the boundary very close to it.
Large gamma, local influence, complex boundary, like a macro lens.
Exactly. Can lead to very wiggly boundaries that might overfit, capturing noise.
So finding the right gamma is another balancing act.
Totally. The default scale tries to do this adaptively based on your data. It calculates gamma as 1, that features x.var. There's also auto, which is just 1 features.
Scale sounds smarter, adapting to the data variance.
It often is. And for poly and sigmoid, there's also coa0, another tuning parameter for those specific kernels.
Okay, so C, kernel, gamma, lots to potentially tune.
Definitely. And one more cool thing. After training, you can inspect the support vectors.
The VIP data points.
Exactly. The ones defining the margin. Scikit-learn lets you see them.
How?
CoolFF.support gives you their indices in your dataset. CLF.supportVectors gives you their actual feature values. And CLF.inSupport tells you how many support vectors there are for each class.
That's really insightful. Knowing which data points are most critical tells you about the boundary.
Exactly. Helps understand the model and the data's separability.
All right, let's put this into practice. Our source material shows 2 experiments on MES, right? Linear versus nonlinear.
Correct. A direct comparison. First, feature scaling, then the SVC. Train, evaluate. Standard process.
Okay, experiment 1, linear SVM. What was the setup?
Used min-max scaler to scale pixels 0, 1, then SVC with kernel linear, and C1, default C.
Simple linear setup. And the results?
Pretty solid, actually. Training accuracy was 91.07%.
Okay. And on the unseen test data,
Overall accuracy was 90%.
90% with just a linear separator in 784 dimensions. That's not bad at all for handwritten digits.
Not bad. The classification report showed details. Like, for digit 0, precision 0.91, recall 0.96, F1 score 0.94, very good. Digit 5 was maybe a bit harder, precision 0.89, recall 0.85, F1 0.87, still decent.
And the confusion matrix. Did it confuse specific digits?
Yeah, it showed some confusion, maybe between visually similar digits like 4s and 9s sometimes.
Yeah.
Expected with a linear model trying to separate those shapes.
Okay, 90% is our baseline with linear. Now, experiment 2, nonlinear RBF kernel. What was the setup here?
Again, SVC, but this time with kernel RBF. And the source used initial parameters, gamma 0.1 and C1, scaling likely similar initially.
RBF, gamma 0.1, C1, intuitively may be better because RBF is more flexible. What happened?
Well, this is where it gets interesting. The performance dropped significantly.
How much?
Training accuracy went down to 82.87% from 91%.
Wow, and test accuracy.
Dropped even more, down to 85% overall from the linear model's 90%.
That's a big hit. Why would the supposedly more powerful RBF kernel do worse? What did the confusion matrix show?
It showed a lot more confusion. Specifically, digits like 4, 5, 6, 7, and 8 were getting misclassified frequently as 2.
As 2. That's weird.
Very weird. The classification report reflected this. For label 2, precision was terrible, like 0.47, though recall was high. 0.99, fifth one score was only 0.63. Some digits like 0 were still okay, but the overall performance suffered badly.
Whoa. Okay, that's counterintuitive. What's the lesson here? Why did the complex kernel fail?
This perfectly highlights the critical need for hyperparameter tuning. That initial choice of gamma 0.1 and C1 was just bad, likely way off the optimal values for MNIST.
So the parameters were wrong.
Almost certainly.
Yeah.
With those settings, the RBF model was either underfitting, maybe gamma was too large, making influence too local, or overfitting in weird ways, or just creating a really poor decision boundary that didn't generalize.
So RBF can be better, but only if you find the right C in gamma.
Exactly. It has the potential to capture the nonlinearities better than the linear kernel, but only with the right tuning. This experiment screams, don't just use default or arbitrary parameters for nonlinear models.
Powerful lesson. Tuning isn't optional, it's essential.
Especially for complex models like RBF SVMs.
Okay, besides SVC, the sources mentioned 2 others, new SVC and linear SVC. How do they fit in?
They offer specialized advantages. SVC is the generalist, these two are specialists.
Let's start with new SVC. Based on libs VM like SVC, but uses new instead of C. What's new?
Right. New is a float between 0 and 1, default often 0.5. It's clever. It acts as an upper bound on the fraction of training errors, margin errors,
Upper bound on errors.
and simultaneously a lower bound on the fraction of support vectors.
Whoa. So new directly controls the proportion of errors and support vectors, like set new 0.1 means max 10% errors and min 10% support vectors.
Precisely. It's a more direct way to think about the trade-off between errors and model complexity, represented by the number of support vectors. Some find it more intuitive than C.
I can see that. It gives you a quantifiable handle on errors and sparsity.
Exactly. Otherwise, parameters are similar to SVC.
Okay, and linear SVC. Built on linear, faster for linear problems.
Yep. Designed for speed and scalability on linear tasks.
Advantages.
More flexibility in penalties and loss functions, scales way better to huge numbers of samples, and it supports both dense and sparse data, which is great for things like text classification, where data is often very sparse.
Sparse data, right. Important for text. Key parameters for linear SVC.
Penalty can be L1 or L2 default. L1 is interesting because it can shrink some feature weights to 0, doing automatic feature selection.
L1 for feature selection. Cool.
Loss can be hinge, standard SVM, or squared hinge, default. But note, you can't use L1 penalty with hinge loss together.
Good to know. C parameter again.
Yes. C for regularization, similar idea to SVC.
And that dual parameter, primal versus dual optimization.
Yeah, it's a bit technical, but the key tip, if you have more samples than features, and samples and features, that dual false is usually faster. If feature samples dual true, default is often better.
Practical tip, nice. And fit intercept.
Just go Boolean. Whether to calculate an intercept term for the line plane or force it through the origin, usually you want an intercept.
So linear SVC is the go-to for massive linear problems, especially sparse ones. Speed and scalability are its game.
Exactly. Your high-performance linear specialist.
Okay, back to that poor RBF result. It clearly needed tuning. This leads us to hyperparameter tuning, and the source highlights grid search cross-validation, right?
Yes, grid search CV. This is how we systematically find those good C and gamma values instead of guessing.
How does it work again? Exhaustive search.
Pretty much. You define a grid of parameter values you want to try, like a list for C, zero point 0.1, 110, 100, and a list for gamma, 0.01.11.
Okay, a grid of possibilities.
Then grid search trains and evaluates an SVM for every single combination in that grid, 0.1 and 0.01, 0.1 and 0.1, and 0.1 and 1, then 1 and 0.01, and so on.
Every combination. Sounds slow.
It can be, and it does this evaluation using cross-validation.
Cross-validation, splitting the data.
Right. It splits the training data into multiple folds, trains on some fold, tests on the remaining one, and repeats. This gives a more robust estimate of how well each parameter combination performs, avoiding getting lucky on one specific test split.
Makes the evaluation more reliable.
Exactly. The source mentions using standard scaler for scaling within the grid search pipeline this time.
Standard scaler. Different from min-max scaler earlier.
Yeah, scales to 0, mean unit variance.
Mm-hmm.
Another common choice, often good if algorithms assume normality or if outliers are present.
Okay. And for cross-validation, it used stratified shuffle split.
Right. Stratified means it keeps the class proportions the same in each fold. Crucial for MNIST to make sure each fold has a good mix of all 10 digits. Shuffle split means it shuffles the data before splitting.
So define the grid, choose the CV strategy.
Then you create a grid search CV object in scikit-learn, pass it your SCC estimator, your parameter grid, param grid, and the CV strategy.
Mm-hmm.
Then you just call .fit on the grid search CV object with your training data. It handles the whole massive search automatically.
And after it runs, maybe for a while,
It tells you the best parameters it found, best params, and the score achieved with those parameters, best score.
brilliant. Brute force, but structured and validated. The source noted it can take quite a long time.
Definitely. Lots of models being trained. But the payoff is finding parameters that should work much better.
And the source challenges us to run it and see if the RBF performance jumps up past the linear model's 90%.
Exactly. The expectation is that a well-tuned RBF kernel, finding the right C and gamma via grid search, should significantly outperform the linear one on a complex visual task like MNIST. It should capture those nonlinear patterns much better once tuned.
Cool. Okay, one more structural thing. MNIST has 10 classes, 0, 9, but SVMs are fundamentally binary, right? 2 classes only. How do they handle 10?
Great question. They use specific strategies to break down the multi-class problem into binary ones. The sources highlight 2 main ways, 1 versus 1, OVO, and 1 versus the rest, OVR.
OVO and OVR, how does SVC handle it?
SVC and USVC typically use OVO by default.
1 versus 1, how does that work?
If you have n classes, OVO trains n1, 2 binary classifiers. Each one learns to distinguish just one pair of classes.
N1. For MNIST with 10 classes, that's 10, 9, 2 equals 45 classifiers.
Exactly. 45 little binary SVMs, 1 for 0 versus 1, 1 for 0 versus 2, 1 for 8 versus 9, every possible pair.
Wow, 45 models. How does it predict them?
When a new data point comes in, all 45 classifiers predict casting a vote for one of their 2 classes. The class that gets the most votes overall wins. It's like a tournament.
Majority vote wins.
Okay.
And linear SVC, does it do the same?
No, linear SVC typically uses OVR, 1 versus the rest.
1 versus the rest. How's that different?
For n classes, OVR trains only n binary classifiers, fewer models.
Just 10 for MNIST.
Right. Each classifier learns to distinguish one class from all the other classes combined. So one model for 0 versus not 0 versus 1 to 9, another for 1 versus not 1 to 0, 2 to 9, and so on.
Ah, 1 versus everybody else. How does prediction work there?
Each of the n classifiers gives a score for the new data point, like how confident it is that it belongs to its positive class. The class whose classifier gives the highest score wins the prediction.
Highest score wins. Makes sense. Does linear SVC have options here?
Yeah, the multi-class parameter can be over, default, or Kremer-Singer.
Kremer-Singer.
It's a more complex approach that tries to optimize all classes jointly, but the source says it's rarely used because it's slower and often doesn't give much better results than OVR.
So OVO trains more models but on smaller subsets, pairs. OVR trains fewer models but each on the full data set, just relabeled. Fascinating trade-offs.
Exactly. Different strategies, different computational profiles.
Okay, we've covered a ton. Core ideas, MNIST prep, SVC parameters, linear versus RBF, tuning, other SVM types, multi-class strategies. Let's zoom out. What are the big picture pros and cons of using SVMs?
Absolutely. Knowing the strengths and weaknesses is key for deciding when to use them.
Let's start with the good stuff. Advantages.
Big one. They're really effective in high-dimensional spaces. Lots of features. SVMs often handle it well thanks to that kernel trick.
High dimensions, check.
Also effective even when dimension samples. When you have more features than data points, Common genetics, for instance. SVMs are good there.
Okay, useful for wide data.
They're memory efficient because the decision only depends on the support vectors. You don't need the whole data set after training to make predictions.
Memory efficient, good for deployment.
And versatile. Different kernels, linear or BF, poly, that let them adapt to different data structures and create complex decision boundaries.
Very adaptable. So great for high dimensions, wide data, memory-sensitive apps, and flexible boundary shapes. Sounds powerful.
They are, especially if you're drowning in features.
But there must be downsides, disadvantages.
Definitely. One is they don't directly output probability estimates. You need the confidence of a prediction, not just the class label.
So like 70% chance it's a 5.
Exactly. Getting that requires an extra computationally expensive cross-validation step during prediction. It slows things down.
Okay, no easy probabilities. What else?
Choosing the kernel and its parameters, see gamma, can be tricky. We saw that with RBF. Bad choices lead to poor performance, especially overfitting if feature samples. Requires careful tuning.
The tuning challenge can be complex and time-consuming.
And related to that, computational cost. Training SVMs, especially with nonlinear kernels on large data sets, can be very slow. Grid search adds even more time.
So potentially slow to train, need careful tuning, and don't give probabilities easily.
Those are the main trade-offs. Power comes with responsibility and computational cost.
Got it. Well, this has been a fantastic deep dive. We've really unpacked support vector machines from the core idea of the maximum margin hyperplane
To seeing them tackle handwritten digits on MNIST.
exploring SVC, new SVC, linear SVC, and scikit-learn, the importance of parameters like C, kernel, gamma,
The need for tuning with Grid Search CV.
and how they handle multi-class problems using OVO or OVR. You really get a feel for how these algorithms work now.
Absolutely. And connecting it to the bigger picture, SVMs are still a foundational, powerful tool in machine learning. Maybe not always the flashiest compared to deep learning now, but incredibly effective for many tasks.
Especially structured data, high dimensions.
Right. You've definitely added a key classifier to your mental toolkit.
So for you listening, you're not just hearing about algorithms, you're building a framework. Next time you see AI doing something smart, recognizing a face, understanding speech, reading handwriting, you'll have a better sense of the clever math like SVMs working behind the scenes.
Which brings us to a final thought. We saw how critical and sometimes computationally heavy tuning parameters like C and gamma is for SVMs.
Right, grid search took time.
So with the rise of more automated machine learning, AutoML, and increasingly black box models, especially in deep learning, it raises a question for you to ponder. How much do we need to understand the knobs and dials, the intricate tuning of every parameter?
Versus just trusting the automated optimization tools.
Exactly. What are the trade-offs there?
Yeah.
Between efficiency and maybe losing some control or interpretability, how does it affect our trust in the system's decisions, especially when these models make choices in really critical areas? Something to think about.